Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read Lead Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1 to Module 3 in my channel. Please do check out if you want to check it out. And Module 4 consists of Time Response Analysis and Stability Analysis. Time Response Analysis I have already completed previously, and some problems also I have done on time response analysis. Now with a new chapter, that is second chapter of module 4, stability analysis, we will see from this video. In the stability analysis, we have again 4 topics, that is concepts of stability, necessary condition for stability, and root stability criterion, and relative stability analysis. First we will see concepts of stability in this video. Under the concepts of stability, first what we will study when a linear control system is subjected to both inputs and initial conditions. The total response is given by what? Zero state response and zero input response. Okay. When a linear control system, is subjected to both inputs as well as initial conditions, the total response will be based on what? The zero state response and zero input response. Zero state response. The zero state response is due to input only. All the initial conditions of the system are zero. Whereas zero input response is due to initial conditions only. All the inputs are zero. Okay, you need to remember that. Then roughly speaking, stability in a system implies that small changes in the system input. Stability is nothing but small changes in the system input, initial conditions, or in system parameters do not result in large changes in system output. If there is some changes in the input, for example, a small changes, it should not affect the output. That is nothing but the stability. If there are more changes, large changes, then the system is not stable. Okay, stability is very important characteristics of transient performance of a system. Okay, an unstable system is useless system. So almost every working system is designed to be stable. For example, if you are using a washing machine, if the washing machine is not working according to the input given, it is not stable, then it is unstable. No, it should work according to the minimal changes is okay, but large changes, something wrong with the washing machine, then it is an unstable system. So any control system need to be stable. The following two notions of system stability are to be satisfied for linear time invariant system. Linear time invariant means what? The system does not vary with time. Time invariant systems to be stable. When the system is excited by a bounded input, the output is bounded. This is called bounded input, bounded output stability. If the input is bounded, then output is also bounded. This concept is called what? Bounded input, bounded output stability. When no input is applied, the output tends towards zero irrespective of the initial conditions. When there is no input applied itself, then output tends towards what? Zero irrespective of the initial conditions. This stability is called what? Asymptotic stability. What it is called? Asymptotic stability. Okay. Now we will see the difference between linear and non-linear system. Equilibrium states. Based on equilibrium state, only one equilibrium state. Non-linear have many equilibrium states. And based on the dependency, depends only on system parameters, not on input or driving function. Whereas may depend on both system parameters and input conditions. Stability with initial conditions. Stable for one set, stable for all initial conditions. But non-linear, stable for one set, may be unstable for another. Okay, as it is non-linear. Stability with bounded input. Stable for one bounded input, then it is stable for all bounded inputs. If it is in non-linear system, if it is stable for one bounded input, may or may not be stable or unstable with another. Definition of stability. Here, well-defined and straightforward. Linear system is well-defined and straightforward. Whereas non-linear systems, difficult to define. No clear-cut response or correspondence with earlier definitions. Generalized techniques. Simple and powerful techniques available to determine stability. Whereas no generalized techniques available for determining stability. Like this, actually in textbook that given in the form of paragraph. To make it easy, I made into a differences so you'll understand how linear and non-linear systems are different based on the aspect. Now we will see bounded input, bounded output stability. What it means. Let R of t, that is input, reference input, C of t, output, correspondence output, and G of t be the input, and G of t be the input output, and G of t is what? Impulse response for linear time invariant system. They are related in S domain. So C of S is what? R of S into G of S. We know this. Output is what? R of S into G of S. Nothing but C of S by R of S is what? G of S. So they know output by input. So you can write this R of S divided by into this side. So C of S is equals to R of S into G of S. So convolution integral relating R of t, C of t and G of t is C of t is equals to integral 0 to infinity R of t minus tau G of tau d tau. Okay, you can write in this way, R of t minus tau G of tau d tau. Okay, in terms of convolution integral, taking the absolute value on both sides of the above equation. Absolute value means what? The modulus. If you take, since the absolute value of an integral is less than or equals to the integral of the absolute value, okay, less than or equals to the absolute value, we can write what? The BIBO is what? Nothing but bounded input, bounded output stability condition is satisfied if for every bounded input, for every bounded, nothing but what? Absolute value R of t less than or equals to m1 less than or equals to infinity, the output is bounded C of t less than or equals to m2 less than infinity. For every bounded input there is bounded output. Okay. Therefore, for a bounded input, the bounded output condition is this. So, thus the notion of BIBO stability is satisfied if the impulse response J of t is absolutely integrable, like this, absolutely integrable, that is finite. That is, the area under absolute value curve of the impulse response J of t evaluated from t equals to 0 to t equals to infinity must be finite. The nature of the impulse response G of t is dependent on both poles of the transfer function G of s, which are the roots of the characteristic equation. These roots may be both real and complex conjugate. Maybe they can be real or complex conjugate and may have multiplicity of various orders. If any of the roots of the characteristic equation is in the right half of the S-plane, if the roots found for the impulse response, the characteristic equation, is the right half of the S-plane, then the transient response increases monotonically with time or oscillates with increasing amplitude. Okay, if there are non-repeated roots of characteristic equation on the imaginary axis, as I told, right half means this is right half, this is left half, and this is imaginary axis. So, if they are on the imaginary axis, the response, if this is on the imaginary axis, the response oscillates with constant amplitude. If there is a single root at the origin, if it is at the origin, then the output is constant amplitude. Then, if there are repeated roots of characteristic equation on the imaginary axis, the response oscillates with increasing amplitude. Okay, if there are repeated roots at the origin of the S-plane, the output increases without bound. Origin of the repeated roots. Repeated roots is different, or single root is different, or non-repeated root is different. For everything, it has its response. Okay. Now we will see some of the impulse response of various terms of closed loop transfer function M of S corresponds to different pole locations. For example, if the poles are here and here, the pole is here, one of the pole minus A, so A by S plus A is the transfer function. So A is what? The pole. Okay, then root is on the negative axis. Why? Because S plus A is on the negative axis. Then if you see A by S minus A means A is on the right. So S is equals to A is the one of the pole which is on the root on positive real axis. Okay, response exponentially decreasing. Response is exponentially decreasing because e power minus 80 it is. E power plus 80 means exponentially increasing. If there are like this, S plus A plus JB, S plus A minus JB, then it is on the imaginary axis, that is JB minus JB. Okay, and there is a minus A this side on the left side. So So complex conjugate roots on the left half of the S-plane. These are not what? These are what? Complex conjugate. Why? Because it has both real part and the imaginary part. So it is called as complex conjugate roots on the left side, left of the S-plane. If we are like this, these are what? If you see S minus A, so it is on the right side of the plane. So then JB and minus JB. So complex conjugate roots on the right of the S-plane. Okay. Then M of t 2 into A into e power minus at cos bt. So cos means what? Cos 0 is what? 1. So it will start from 1. High amplitude. Okay. Response is damped oscillatory. So if it is cos bt, then the response is exponentially increasing sinusoidally. It is increasing and it is decreasing like that. Then you have what? Single pair of roots on the imaginary axis. A single pair. They, like this means it is a single pair. It is not complex conjugate. It is a single pair like JB and minus JB. If it is like this, then double pair of roots on the imaginary axis. Why? Because S plus JB whole square, S minus JB whole square. So double pair it is present. So then 2A cos BT. It is response is oscillatory. The response is linearly increasing sinusoidal. Linearly increasing sinusoidal. Then single root at origin. At origin it is a single root. Why? Because A by S. S is equals to what? 0. The pole is at the origin. S square. Double root at the origin. Why? Because S square is present. Two poles. It is two roots. So the response is what? Constant. There is no change in the response. If the response is like this, the response linearly increases with time. These are different concepts of how the responses are seen in how the roots are mapped on this plane is shown in this all the images. So the following general conclusions can be drawn regarding system stability. Based on the previous examples, previous images, we can draw some conclusions. So if all the roots of the characteristic equations have negative real parts, then the impulse response is bounded and eventually decreases to what? 0. Therefore, integral 0 to infinity g of tau d tau, that is the impulse, integral of the impulse is finite and the system is bounded input, bounded output stable. Then if any root of the characteristic equation has a positive real part, g of t is what? Unbounded. See, if it is negative, it is bounded input, bounded output. If it has a positive real part, if it has a positive real part, that is plus s, g of t is unbounded and it is infinite, the system is therefore unstable. If it is on this side, it is unstable, and if it is this side, it is stable. This is unstable and this is stable. Okay. If the characteristic equation has repeated roots on JW, that is nothing but imaginary axis, g of t is unbounded and it is infinite. Okay, and the system is therefore again unstable. If one or more non-repeated roots of the characteristic equation are on what? Imaginary axis, then the g of t is bounded and g of tau into d tau is infinite. The system is therefore again unstable. Only if the if it is on the negative real parts, the roots are of the characteristic equation on the negative real parts, this is left side, not the negative real parts, then it is stable, bounded input, bounded output. This is the conclusion. Okay, you need to know these conclusions, so only you can understand whether it is stable, not stable, unstable. You'll understand. Then we will see what? For analysis and design purposes, stability may be classified into two. What are those? Absolute stability and relative stability. What is absolute stability? It is what? It is a qualitative measure of stability. Whereas relative stability is what? Quantitative measure of stability. Qualitative means it is based on quality. Relative means based on the quantity, the numbers. It is a yes or no answer. Absolute is what? Either it is yes or no. It refers to the condition of whether the system is stable or not stable, yes or no. Okay, then once the system is found stable, it is of interest to determine how stable it is, and this degree of stability is measure of relative stability. Okay, it is a quantitative measure of how fast the transients die out in the system. How transients die out in the system, it is a quantitative, whereas here absolute it is either stable or not stable, either yes or no answer type stability it is. So Then we will see the relative stability may be measured by relative settling times of each root or pair of roots. Relative stability means what? Relatively the settling times of each root or pair of roots is measured. Where the roots are settling, that time is measured. That is what? Relative settling time. Relative stability. The settling time of poles is inversely proportional to the real part of the roots. The settling time of the poles, whatever poles are there, no, it is inversely proportional to what? Real parts of the roots. As a root or a pair of roots moves farther away from the imaginary axis. As you know, this is the imaginary axis. If the roots move farther away from the imaginary axis, then the relative stability of the system improves. Okay, it should move away from the imaginary axis. Then the stability will increase. Understanding, if this is the imaginary axis, the poles should be away from this imaginary axis. Then it is more relatively stable. Okay, if all the roots of the characteristic equation have negative real part, the system is stable. As I told in the previous one also, that all the roots should be on the negative real part, negative side, so that the system is stable. If any root of the characteristic equation has a positive real part, which is on the right side, then there is a repeated root on the j, or if there is a repeated root on this j omega axis, that is nothing but what? Imaginary axis, the system is again unstable. If all the roots of the characteristic equation have negative real parts except for the presence of one or more non-repeated roots on jw axis, the system is limitedly stable. It is limitedly stable. There are almost all the roots are on the negative only. Whatever we want on the negative, it is correct. It is stable. But there are one or more, except for the presence of one or more non-repeated roots. There are some non-repeated roots which are present on the imaginary axis. So the system will be limitedly stable. Limitedly stable. Okay. In further subdivision of the concept of stability, a linear system is characterized by what? Absolutely stable with respect to a parameter of the system if it is stable for all values of the parameter. When it is called absolutely stable, if all the parameters of the system are stable for all the values of the parameter. Conditionally stable with respect to a parameter if the system is stable for only certain bounded ranges of values of this parameter. See, absolutely stable means for all the values of the parameter it is stable, but conditionally means for particular condition only it is stable, for other it is not stable. Maybe at the range or a range of values, the parameter, it is stable. So it is a conditionally stable. These are the concepts of stability, so that you should understand. Like if the S-plane is in like this way, if the S-plane looks like this, I'll take one more color. If you see this is the S-plane, and this is a positive, sorry, okay, this is a negative S-plane, this is positive S-plane, this is a positive imaginary axis, negative imaginary axis. The root should be on the left plane, then it is stable. If it is on the right side, it is unstable, and if it is also on the imaginary axis, it is not stable. If all the roots are on the left side and some of the non-repeated loops, one or more non-repeated loops, if it is on the imaginary axis, then it is limitedly stable. So these are some of the concepts of stability you need to know. We should understand the concept first before dwelling into these sums. Why we are studying the stability, what are the concepts. So this video consists of the concepts of the stability, different concepts, how stability is analyzed. Okay, so by this the concept of stability is done. So in the next video I'll continue the other topics. For now, I'm stopping the video. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.